Hello students, today we are going to work out problems from chapter 6 Electromagnetic Induction. A rectangular wire loop of sides 8 cm and 2 cm with a small cut is moving out of a region of uniform magnetic field of magnitude 0.3 Tesla directed normal to the loop. What is the EMF developed across the cut if the velocity of the loop is 1 centimeter per second in a direction normal to the longer side, shorter side of the loop? For how long does the induced voltage last in each case? So you can imagine a rectangular wire loop. Its length is 8 centimeter, its breadth is 2 centimeter, it has a small cut and it is moving out of a uniform magnetic field. The strength of the field is 0.3 Tesla and it is perpendicular to the loop. Now we have to find out what is the EMF developed across the cut if the velocity of the loop is 1 centimeter per second and it is perpendicular to the longer side. Next, we have to find out what is the EMF developed across the cut when the motion is perpendicular to the shorter side. And how long does the induced voltage last in each case? Of course, you know the induced voltage will last only as long as the coil or the loop remains inside the magnetic field. Okay, so let us do the first part. Area of the rectangular loop is given by length into breadth. Since length and breadth are given in centimeter, we have to convert it into meters. So area is 16 into 10 to the power minus 4 meters squared. Now, formula for EMF developed in the loop when the motion is perpendicular to the longer side. So E equal to BLV. B is the magnetic field, L is the length of the coil, and V is the velocity. So we get your answer as 2.4 into 10 to the power minus 4 volt. Now when the velocity or the motion is perpendicular to the longer side, then the shorter side will be parallel to the direction of motion. And the shorter side, as long as the shorter side or the breadth remains in the magnetic field, the induced voltage will last. So when you calculate the time taken to travel, you have to calculate distance traveled as breadth. The breadth divided by velocity, because now breadth is parallel to the direction of motion. So you get your answer as 2 seconds. So the induced voltage is 2.4 into 10 to the power minus 4 volts and it lasts for 2 seconds. Similarly, the EMF developed when the direction of motion is perpendicular to the shorter side. It is given as E equal to B into breadth into velocity. And you get your answer as 0.6 into 10 to the power minus 4 volt. Here once again the length will be parallel, or the longer side will be parallel to the direction of motion. So we can calculate the time as distance traveled by velocity, which is longer side by velocity, and you get your answer to be 8 seconds. So for the second part, the induced voltage is 0.6 into 10 to the power minus 4 volts and it lasts for 8 seconds. Next question. Suppose the loop in exercise 6.4 is stationary, but the current feeding the electromagnet that produces the magnetic field is gradually reduced so that the field decreases from its initial value of 0.3 Tesla at the rate of 0.02 Tesla per second. if the cut is joined and the loop has a resistance of 1.6 ohm, how much power is dissipated by the loop as heat? What is the source of this power? Now, exercise 6.4 is the problem that we just completed. In exercise 6.4, the loop was in motion. But now we consider the loop to be stationary. So the area of the loop will be considered as a constant, and the variation here is for magnetic field. So we have to take dB by dt here. So area, of course, is length into breadth from the previous problem. 8 into 2, convert it into meters, you get 16 into 10 to the power minus 4 meters squared. Now, initial value of the magnetic field is 0.3 Tesla, and the magnetic field is decreasing with time at the rate of 0.02 Tesla per second. So, EMF can be induced by varying magnetic field. So, E equal to d phi by dt, and phi here is A into B, where A is area and B is magnetic field. And since the loop is stationary, we consider A as constant taken outside, no variation with time, A into dB by dt. So we have the values of A and we have the values of dB by dt, and hence we can calculate the EMF induced is 0.32 into 10 to the power minus 4 volt. So resistance of the loop is given in the question as R equal to 1.6 ohm. So what is the current induced in the loop? I equal to E by R. And if you substitute the values, you get the current to be 2 into 10 to the power minus 5 ampere. From that, we can calculate the power dissipated is equal to I squared R. So we have the value of I, we have the value of R, and therefore the power dissipated is 6.4 into 10 to the power minus 10 watts. W-A-T-T-S, watts. And the source of power is an external agent which is responsible for changing the magnetic field with time. The coil is stationary, but the magnetic field kept decreasing with time. That was done by some external agent. And that same external agent is responsible for the power dissipation in the coil. Next question. A square loop of side 12 centimeter with its sides parallel to x and y axis is moved with a velocity of 8 centimeter per second in the positive x direction in an environment containing a magnetic field in the positive z direction. The field is neither uniform in space nor constant in time. It has a gradient of 10 to the power minus 3 Tesla per centimeter along the negative x direction. That is, it increases by 10 to the power minus 3 Tesla per centimeter as one moves in the negative x direction. And it is decreasing in time at the rate of 10 to the power minus 3 Tesla per second. Determine the direction and magnitude of the induced current in the loop if its resistance is 4.50 milliohm. Small letter m, so milliohm. So here we have a square loop. So all sides are equal, 12 centimeter, with its sides parallel to x and y axis. That means it is placed parallel to the xy plane. And it is moving with a velocity of 8 centimeter per second along the positive x direction. So there is a magnetic field which is in the positive z direction. That means a perpendicular magnetic field to the xy plane. Now this magnetic field varies with distance. That is why it has a gradient. A gradient is dB by dx. The denominator is dx. and along the negative x direction. Second, it decreases in time. So we have dB by dt. So 10 to the power minus 3 Tesla per second. So we have for the magnetic field dB by dx, which we call as the gradient, and we have its variation with time, that is dB by dt also. So what is the rate of change of magnetic flux due to the motion of the loop in a non-uniform magnetic field? Now flux is denoted by phi. So if you look at the left side, you can see d phi by dt equal to A into dB by dx into V. Now how do we get that? That is shown on the right side. D phi by dt is d by dt of AB. A stands for area of the coil and B stands for magnetic field. Now here A is constant and dB, magnetic field, varies with respect to time. So we have dB by dt. But in this particular problem, magnetic field varies with space as well as with time. So we have to bring these two into the picture here. So we have A into dB by dx into dx by dt. If you look at that formula, actually the numerator dx and the denominator dx will cancel. But we are just splitting it into that form. dB by dx we will leave as it is, but dx by dt we will write as velocity, because velocity is rate of change of displacement. So we get d phi by dt equal to A into dP by dx into V. Now all these factors are given in the question: area of the coil, then the gradient, magnetic field gradient dB by dx, and velocity. So you get your answer for rate of change of magnetic flux as 11.52 into 10 to the power minus 5 Tesla meter squared per second. So this is one part. Now rate of change of flux due to time variation in the field is given as d phi by dt equal to A into dB by dt. It is directly time variation dB by dt. So we have already the area is 144 into 10 to the power minus 4 and dB by dt is given as 10 to the power minus 3. So you get your answer to be 1.44 into 10 to the power minus 5 Tesla meter squared per second. So what is the total change, rate of change of flux is the induced EMF in the circuit, in the coil. So the total induced EMF in the square loop is, you will have to add the rate of change of flux due to the space gradient variation and due to time variation of the magnetic field. So when you add these two answers, you will get the total induced EMF to be 12.96 into 10 to the power minus 5 volt. Now, induced current. What is the current that is induced in the circuit? I equal to E by R. Resistance is given as 4.5 milliohm. So conversion with 10 to the power minus 3. And current is calculated as I equal to 2.88 into 10 to the power minus 2 ampere. Hence, we get current to be a positive answer. So the direction of induced current is such that there is an increase in the flux through the loop along the positive Z direction. Next question. It is desired to measure the magnitude of field between the poles of a powerful loudspeaker magnet. A small flat surge coil of area 2 cm squared with 25 closely wound turns is positioned normal to the field direction and then quickly snatched out of the field region. Equivalently, one can give it a quick 90-degree turn to bring its plane parallel to the field direction. The total charge flown in the coil measured by a ballistic galvanometer connected to the coil is 7.5 millicoulomb. The combined resistance of the coil and the galvanometer is 0.50 ohm. Estimate the field strength of the magnet. So basically we just have to find out what is the field strength of the magnet. We have to just find out what is the field strength of the magnet. So here we have a surge coil of area 2 centimeters squared. We have to convert that into meters. There are 25 closely wound turns and its field direction is quickly changed. So the total charge flown in the coil is 7.5 millicoulomb. Then the combined resistance is given. We have to find the field strength of the magnet. So first we will see what is the formula for induced current in the coil. Induced current is induced EMF by resistance. And induced EMF is given as E equal to minus N d phi by dt. So if you combine those two equations, we get I equal to minus of N d phi by dt by R. Or if you cross multiply, you get I dt equal to minus N by R d phi. So if you integrate this equation 3 on both sides, we get integral I dt equal to minus N by R integral d phi. Now d phi, the limits are the initial flux and the final flux. Initial flux through the coil is given as B into A, magnetic field strength into area of the coil. Final flux through the coil is 0 because we are removing the coil out from the magnetic field as per the question. But the left side integral I dt is the summing up of all the charges Q. So we can write it as Q. So we can change our equation to Q equal to minus N by R, and after integrating d phi we get in brackets phi F or the final minus phi I. So final flux minus initial flux, which is change in flux. So you get equal to minus N by R minus phi I. Because you know final is 0. 0 minus phi I. So this leads to plus N phi I by R, and phi initial flux is B into A as mentioned earlier. So we get Q equal to NBA by R, or field strength is asked in the question, B equal to Q into R by NA. So substitute all the given values from the question and you get B equal to 0.75 Tesla. Hence the field strength of the magnet is 0.75 Tesla. Next question. The figure 620, that is the figure that is shown in the question, shows a metal rod PQ resting on the smooth rails AB and positioned between the poles of a permanent magnet. The rails, the rod, and the magnetic field are in three mutual perpendicular directions. A galvanometer G connects the rails through a switch K. Length of the rod is 15 centimeter. Magnetic field B is 0.50 Tesla. Resistance of the closed loop containing the rod is 9.0 milliohm. Assume the field to be uniform. Now we have 7 questions for this particular diagram. So we'll work out each one by one. So before we start on the first question A, let us analyze the question and the diagram. You have a metal rod PQ as you see in the diagram. So Q is at the near end and P is at the far end. and the arrow mark which is vertically downwards on the left side of PQ shows the direction of magnetic field because the magnetic field acts perpendicular to the rod. So it is perpendicular. And on the right side, the arrow mark on the right side shows the direction in which PQ is moving. All right. So we have now a metal rod PQ resting on smooth rails. You can see the two parallel rails A and B. The rails, the rod, and the magnetic field are in three mutually perpendicular directions, as you see. So we have to assume the field to be uniform also. So let us see the first question. Suppose K is open and the rod is moved with a speed of 12 centimeter per second in the direction shown. Give the polarity and magnitude of the induced EMF. So these are the questions. Is there an excess charge built up at the ends of the rods when K is open? What if K is closed? I will read the questions and then come back to the answers. C. With K open and the rod moving uniformly, there is no net force on the electrons in the rod PQ, even though they do experience magnetic force due to the motion of the rod. Explain. D. What is the retarding force on the rod when K is closed? E. How much power is required by an external agent to keep the rod moving at the same speed when K is closed? How much power is required when K is open? F. How much power is dissipated as heat in the closed circuit? What is the source of this power? G. What is the induced EMF in the moving rod if the magnetic field is parallel to the rails instead of being perpendicular? So I read out the 7 questions. I'll read out each question one by one and work out the answers. So the data given in the question: length of the rod 15 centimeter, magnetic field strength 0.50 Tesla, resistance of the closed loop is given as 9 milliohm, induced EMF is 9 millivolt, speed of the rod V is given as 12 centimeters per second. So the first question: suppose K is open and the rod is moved with a speed of 12 centimeter per second in the direction shown. Give the polarity and magnitude of the induced EMF. So when K is open, that means no current is passing through the circuit. There is no circuit. It is only the three perpendicular things over there. So polarity is such that end P shows positive and Q will be negative as per Fleming's left-hand rule. And the EMF induced will be given by the formula E equal to B into V into L. B stands for magnetic field, V stands for velocity or speed, and L is the length of the rod. So when you work out, you get the induced EMF as 9 into 10 to the power minus 3 volt. It is capital V volt. Second question. Is there an excess charge built up at the ends of the rods when K is open? What if K is closed? So the answer will be yes. When K is closed, excess charge is maintained by the continuous flow of current. When K is closed, obviously, as you can see from the diagram, a current circuit, the EMF induced will produce a current, and that excess charge is maintained by the continuous flow of current. And the current induced is given by the formula I equal to E by R, which is 1 ampere. Now what happens when K is open? When K is open, there is excess charge built up at both ends of the rods. The charge will be stored at both ends of the rods. Now C, the question for C. With K open and the rod moving uniformly, There is no net force on the electrons in the rod PQ, even though they do experience magnetic force due to the motion of the rod. Explain. So there is no net force on the electrons in rod PQ when K is open and the rod is moving uniformly. This is because the magnetic force, that is Lorentz force, is cancelled by the electric force that is set up due to the excess charge of opposite nature at both ends of the rods. You know, at P and Q, opposite charges are set up so that electric force, and the rod PQ is in motion. So there will be an electric force set up. That electric force gets cancelled by the Lorentz magnetic force. So there is no net force on the electrons in the rod PQ when K is open. The next question D. What is the retarding force on the rod when K is closed? So retarding force is given by the formula F equal to IBL. And I is E by R. You know it is already 1 ampere. B is the magnetic field and L is the length of the rod. So you get I equal to 75 of, force is equal to 75 into 10 to the power minus 3 Newton. The next question E. How much power is required by an external agent to keep the rod moving at the same speed when K is closed? How much power is required when K is open? So when K is closed, the power required is force into velocity. And you get your answer to be 9 milliwatts. And when K is open, no power is expended. Alright? Because there is no force. F. How much power is dissipated as heat in the closed circuit? What is the source of this power? So the power dissipated as heat is I squared R, and I we had already calculated as 1 ampere and R is 9 milliwatts. So you get your answer again to be 9 milliwatts. The source of this power is an external agent. The last question. What is the induced EMF in the moving rod if the magnetic field is parallel to the rails instead of being perpendicular? So if the moving rod is parallel to the rails, then there will be no EMF induced because the rod does not cut across the field lines. So the rod has to be perpendicular to the field lines for an EMF to be induced. Okay, students, we'll continue in the next class. Thank you so much.